Hello, welcome to the lecture on work and energy. So we'll start with introducing the basic energy model, which defines a system. And it's very important that we always know what the system is, whether you're external or internal to the system. And we will be looking at different forms of energy. Now, it's difficult to define energy because it's an abstract quantity. It's really just a bookkeeping method. And there are just a bunch of formulae that you calculate, but it has this fantastic property that when you calculate all these numbers and add them together, it remains constant if you're in an isolated system. So we will define these terms and then we'll see how we'll use them ultimately for conservation of energy problems. So the important forms of energy that we'll be looking at in this course will be kinetic energy, gravitational potential energy, and elastic energy. That's when you have a spring or a bungee cord. And then we'll also look at heat, because heat is a very common form of energy that you must account for when you're doing conservation of energy problems. So if you're within an isolated system, energy can turn from one type to another. So kinetic energy can become gravitational potential energy or elastic energy, and vice versa. Now, the concept of work is that if you want to change the total energy of a system, then something has to do work on it, or the system has to do work on its environment. And so this is a mechanism for transferring energy in and out of isolated systems. And so here's some examples of somebody doing work. So the athlete does work on the shot, giving it kinetic energy. Somebody strikes a match and the work they do turns into thermal energy. Or a boy using a slingshot, he takes elastic potential energy and stores that up by doing work on that, whatever's in the sling. Okay, so let's define work more formally and see how we're going to use it. So work is, like I said, done by external forces. It always involves a force if you're going to do work. It also always involves displacement. Something has to move if work is being done. So it's not like just, it's hard work to do your homework, or it's hard work to stand and hold a 10-kilogram mass stationary. But as far as the physics definition of work goes, those don't count. Okay, so here's the equation. Work is force times distance. So I want to define these units. So the W is work. The units for work are joules. F is force in newtons. And D here is going to be distance. Now they say displacement, but in this particular equation, it's actually, okay, we'll say displacement, and this will be in meters. Oops. I wonder what happened there. Okay, now force is definitely a vector. Displacement is also a vector. At a higher level course, we would actually write this as what's called a dot product, which is a nice, concise mathematical way of handling all the subtleties of the definition of work. But here we'll just take it separately. For now, just two scalar quantities to get the work. And so this then defines the joule. So 1 joule here is 1 Newton meter. Okay, so let's do an example. We have a dog pulling some weight across the snow. We're told the displacement 4.9 meters. And we have the force is 350 newtons, and we want to know how much work does the dog do. So work is force times, in this case, just distance. And the force in this example was 350 newtons. And the distance moved was 4.9 meters. And so that works out to 1,700 joules. A joule actually isn't that much energy. So you do tend to get pretty big numbers when you're calculating joules. Now, it's very important that when we use this equation, that this force was in the same direction as the displacement, and we were able to just use those scalar quantities. Okay, and that was a positive number. Now, if the force does not act in the direction of the displacement, then you have to take the component of the force parallel to the displacement. So that's what this means. This means component parallel to displacement. Okay, and if you have the angle between the force and the displacement, so down here, if you have this angle theta, then that component here is F cosine theta. Okay, so if the force is not parallel to displacement, you have to take F cosine theta. So this is another version of the equation. In fact, I would use this all the time, F d cos theta. If they are parallel, just put theta equals 0, and the cos of 0 is 1. And so this is a safe equation to use for all problems. Now, work can be positive, negative, or 0. And it all depends on the relationship between the force and the displacement. It is not either of them independently, it's their relationship. So in this case, so problem 1, the force is parallel to the displacement. So you see here the angle is 0. The cosine of 0 is 1. And so that's why we can just write force is work. Sorry, work is force times distance if they are parallel. Now this next one, if they're not parallel, and so here we have an angle less than 90. Okay, so here's the displacement vector pointing horizontally to the right, but the force vector is not horizontal, it's pointing up at an angle. And so this is when we have to use FD cosine theta. Now, if this angle is less than 90, the cosine of theta is positive. Okay, so this would be positive. And you can just test it out in your calculator. From 0 to 90, the cosine is a positive number. Now, if it happens that the force acting on something is up, but the object moves to the right. Now, clearly, it's not that force making the object move to the right. There's something else making it move to the right. But this particular force, like if you're holding a suitcase and walking across the floor, is the force of friction making your body move to the right, which actually moves the suitcase as well. But in this case, because the angle is 90 degrees, and if you punch in your calculator, cosine of 90 is 0, this does no work. Okay, so there's no work done if the force is 90 degrees to the direction of motion. We're going to see that the way you figure out whether work is positive, negative, or 0 is if the force is trying to speed up the object. Now, whether it succeeds or not doesn't matter, but if it's trying, that's positive work. If it's trying to slow the object down, that's negative work. If it's doing neither speeding up nor slowing down, that's 0 work. And so if you push perpendicular to the way something's moving, you're never going to speed it up or slow it down. And that's why this work is 0. Here, notice how this force, this is trying to slow it down, that the object's moving to the right, but this force tends to be left. And so now when you put in the angle greater than 90, so like just try it out, put 120 degrees in here, you're going to get a negative number for cosine of 120. And so this work is negative. And that's because it's trying to slow this object down. Okay, now the reason it's moving to the right is because either somebody gave it a shove and it's just sliding till it stops, or because some other force is pulling it to the right. But you can calculate the work from individual forces. You do not have to get the net force to calculate work. Okay, and here's an example when it's exactly anti-parallel. This would be like friction. So this is when theta is 180 degrees, cosine of 180 is negative 1, and so the work done is negative here. Okay, so here it says the sign of work is determined by the angle between the two. Okay, let's do another example now. We have a force exerted at 45 degrees pulling this suitcase over to the right. Okay, and we want to know how much work does that force of tension in that strap do as this. Now, the fact that it's moving at constant speed here, it doesn't really matter. We're just worried about what is the force by this one, what is the work by this one force? Okay, if there's other forces like friction, normal force, gravity force, we don't care about all those. We're just worried about this guy. Okay, so we just use the formula that work is force times distance times the cosine of theta. Okay, and the force on that strap, they said, was 20 newtons. The distance, now this is the distance, just the total distance along the floor that it moves. And that distance was 120 meters. And the angle between those two was 45 degrees. Okay, so when you punch that out, you get 1700 joules again. Okay, it's positive. That strap is trying to speed the suitcase up. Whether it succeeds or not doesn't matter. It is in the direction of motion, so it's trying to speed it up. Now, there are some forces, as I said, that do no work. If you don't move, so if this D is 0, stationary, that's really hard to do, but you're not doing any work on that barbell, okay? The only time that work is happening is if there's motion, okay? So no displacement, no work. And then this is the case of carrying a suitcase. So even though the force that you have to exert is up, as you walk along perpendicular to that force, you're not doing work on the suitcase. You are not, this will not speed up or slow down the suitcase. This force won't. You can speed up the suitcase if you're worried about the force here of friction that moves you across the room. If you start running, then you're going to speed up the suitcase. Okay, so now we'll get into the different types of energy that we'll ultimately be using for conservation of energy. So kinetic energy first. There's the definition. You've probably seen this before. So K, now I may accidentally put KE because I'm used to using KE for kinetic energy, but I'll try to stick to this. Okay, so K is kinetic energy equals this. And the units for that are joules. Okay, all forms of energy have the units, the SI units of joules. There are other units like calories, BTU, things like that, but we're just going to stick to joules. Okay, M is mass in kilograms, and it has to be in kilograms if you're going to get joules for your final result. And V, now this is speed, not velocity. This is the magnitude of velocity. So this is speed in meters per second. Okay, so this now, we just saw that a joule was a Newton times a meter when we define work, because work comes in the same units as energy. They're all joules. So we know that this is a Newton times a meter. Well, if you remember from Newton's second law, F equals ma. A Newton is a kilogram meter per second squared. Multiply by a meter, and the base units for a joule are kilogram meters squared per second squared. Now look up here at this formula, half mv squared. M would be the kilograms, V squared would be the meters squared per second squared. So this is a way to double check all the formulae for energy. They all have to break down to kilogram meters squared per second squared, and that is a joule. So it's called translational kinetic energy, the type we'll be looking at in this course. Now there is something called rotational kinetic energy, but we don't get into that in this course. So all of our objects are just going to be going in straight lines. You know, they could be going down an incline or up an incline or over a hill, but it is still a straight line. Okay, so it's the energy of motion in a straight line. Now, this is related to the work done on the car. So if you look down here, remember this is our kinematics. If the car is speeding up, so this is an example of speeding up. If the force is to the right and the displacement is to the right, that would be positive work. So this car would speed up. And so if you did the kinematics, there would be an acceleration here. Now look what happens if I multiply this whole formula by half m. So I just put a half m there and a half m here and a half m there. So we get 1/2 mvf squared, 1/2 mvi squared. The half and the 2 here cancel. M times a is force. delta x, displacement, is distance, and look what we get. Final kinetic energy, 1/2 mv squared, equals initial kinetic energy plus, and there it is, force times distance, work done, which happens to be, in this case, just force times distance here. But this is a general result. So that's kind of just a funny little way to define that. You don't necessarily have to go through that derivation. If there's no change in any other kind of energy, like potential or elastic, then this work is equal to change in kinetic energy. And this is a very fancy thing called the work kinetic energy theorem, and it's very important. So this just goes through the positive, negative aspect of work and whether or not something will speed up. And so there's no friction. That's very important that we're talking about no friction. And so the only force doing work here is somebody pushing on the block. And if it's down here, so if you push to the right, so there's the force of you pushing here, there's its displacement, that's positive work, the object will speed up. Okay, so I think that's kind of obvious. Now, if the thing is moving to the right, and it's moving to the right because it was already moving before you started pushing on it, there is no friction here. But if you try to slow it down, even though it's moving to the right, you're going to be doing negative work. We've already seen that. And this negative work means it's going to slow down. Okay. Now, if this thing is sliding along this frictionless surface and you push down on it here, well, that's neither speeding it up nor slowing it down. That's an example of zero work done. That's because of this angle. Remember, this would be theta, would be 90 here. Cos of 90 is 0. This theta would be 180. Cos of 180 is -1. And this theta would be 0. Cos of 0 is 1. So it all fits together with the equation. And this, no change in speed. Okay, so let's do an example of how we're going to find speed when we're given a force and a mass. Okay, so this is a couple of horses pulling this canal boat. So they're walking along on the towpath beside the canal. The ropes are attached to this boat and they're just plodding along, pulling it. Now, it takes a fair bit of work to get the thing going, to get the boat going. But once it's going, there's not much friction from the water, not much drag. And so it's not so difficult to keep it going, but it's definitely difficult to get it going. Okay, so this is a question of just how far do they have to walk applying this force until it's up to its speed it wants. And then it can just kind of slack off a little bit and plod along to keep it going. Okay, and it says that it's a nice straight line, so we don't have to worry about theta in this. Okay, so we've got this boat that's being pulled by a force. It's a pretty big force here. It's what's the force? 1400 newtons. We want to know just how far it's going to go. If here it starts from rest, so VI is 0, and then over here, same force, but now it's moving at its final speed of 0.7 meters per second. So it's not going too fast. But it's a big mass, so it does take a fair bit of walking along to get it going. Okay, so the work energy theorem, W, is change in kinetic energy. Okay, and a change means the final kinetic energy, 1/2 mvf squared, minus the initial kinetic energy, vi squared. In this case, this is 0 because the thing's at rest. Okay, and then the work is force times distance. So we have this equation, force times distance is 1/2. Now you could work this question out using kinematics. You could work out an acceleration, and then you could use your kinematic equations. But we saw that that just converts to this formula, and this is much easier and handier formula. Okay, we're trying to find D. So D must be 1/2 mv final squared divided by the force. So it's half, it's a big mass, 55,000 kilograms, I believe was the number. And And then final speed 0.7, don't forget to square it, and then divide by that force, which was 1400 newtons. And turns out you have, those horses have to pull for a distance of 9.6, so 10 meters, not that far. Okay, to get that canal boat up to speed. Okay, now here's another example. Now, this is an important example because that work energy theorem, if you've got more than one force trying to speed up or slow down the object, its change in speed depends on that net force, okay, or the net work. So you have your choice. You can either do, so the work energy theorem is actually that it's W net is delta K. Okay, so this is 1/2 mv final squared minus, it starts from rest, so this, in this case, it's -0. But this is net. Okay, so we need, when we're doing net force, remember this ball is being lifted, it's got the force of gravity on it. Okay, so somebody's lifting like this, force of tension, and that is 2.35 newtons. So that's trying to speed it up, but it's got the force of gravity, which is trying to slow it down, which is mg, which the mass was 200 grams, so that's 0.2 kilograms times 9.8 newtons per kilogram. So that's 1.96 newtons. Okay, now it is the net result of these two that determine what its final speed will be. So we'll do, well, we have two choices. We can do W net is F net times D. F net is up minus down. So it'll be 2.35 minus 1.96 times D. Now, does it tell us how far? Yep, it's going to go up a distance of 1.75 meters. So this is given as 1.75 meters. Okay, so we want the speed. So this is going to be 1/2 mv squared, but let's just get this. Okay, well, that's fine. So that's the network. And now we know that that network, so we've got 2.35 minus 1.96 newtons times 1.75 meters is 1/2 mv final squared, and this is what we're after. Okay, so we will, the mass here is 0.2 kilograms. Okay, so if you put that in and solve, you get a final speed, don't forget to take the square root in the end, of 2.61 meters per second. So that's how fast it would be moving after it was pulled upward. So it would be accelerating the whole time. The force up is bigger than the force down. So this thing keeps speeding up, and it's the distance that determines what its speed is at any given location. Okay. Now we're ready for potential energy. So that was kinetic energy, now potential energy. I think I might stop there.